Okay, so I have decided to do a couple out of chapter 4. I'm going to do one like this and one like this. And I'm just, again, I'm trying to do what I think will be the most helpful for you. You're probably pretty well, you're probably doing pretty good on the more recent stuff. Like we just had test 3, so I wasn't going to go out of my way to review the more recent stuff unless you specifically ask me. Um, so yeah, maybe that's why I chose chapter 4. Also, I didn't choose chapter 3 because these are skills that come up all the time anyway. Um, so then, yeah, this is the first one I wanted to do. Um, you've got 3 vectors, and the question is, are they linearly independent or linearly dependent? And you have the follow-up question. If it's linearly dependent, write the 0 vector as a non-trivial linear combination. Um, there's a couple ways to do this. I'll show you the way that I like. Right, you don't have to really write down this first part, but what we're really doing with this method is we're trying to write, whoops, this is a plus sign, we're trying to write the 0 vector, oops, I'm really messing up, this should have an x3 on it. We're trying to write the 0 vector as a linear combination, where it's this vector times x1, this vector times x2, this vector times x3. Of course, what we usually do is we jump straight to this, which is what I would normally recommend. So you're solving this system, basically. If the only solution is x1, x2, and x3 are all 0, then you say it's linearly independent. And if there is another solution, then you say it's linearly dependent, and whatever that solution is tells you the non-trivial linear combination to get the 0 vector. So let's just solve this. I would like a 1 here. The easiest way for me to do this is to just swap 2 rows. Then I'm going to get 0 here and here. So row 2 minus 3, row 1. Row 3 plus 2, row 1. So that'll give me this doesn't change, and then this is 0. 1 plus 3 is 4. 3 minus 15 is negative 12. This is 0. 1 plus negative 2 is negative 1. Negative 7 plus 10 is 3. And then this is 0. Right? Next thing I would want is a 1 here. There's a couple of things I can do. I could swap rows because I like a negative 1, and then I would run a negative sign through this. But also, like, I noticed that this whole row is divisible by 4, so I'm not going to make fractions if I just divide it by 4. I'll just do that. And now it seems I can see at least what the answer is going to be. It looks like I'm going to 0 this row out in 1 step, because I'm about to do row 3 plus row 2 to make this a 0, but when I do that, that's also going to make this a 0, and then this whole bottom row is going to be a 0. And that's going to mean that it is linearly dependent. Actually, okay. What I just said is true. Let me do another thing. I would actually like to get this matrix in reduced row echelon form, meaning I'm going to get a 0. I'm going to use this one to get a 0 above and below. So for row 1, let me actually write 1, 0, 2, 0. And then this, and then this is a 0 row. And I like that better because, so where are we? This is free. So I'm going to set x3 equal to t. And I like the fact that this is in reduced row echelon form because this is now very easy for me to solve. x1 is just negative 2t, and x2 is just 3t. So I've got negative 2t, 3t, 1, or whoops, t. So let's take a step back and see what we were doing. This was a linearly independent or dependent question, and the way we set this up, we were looking for a solution x1, x2, and x3. And remember what we said, if the only solution was for them all to be 0, then we would say linearly independent. But that's not what happened. This is the solution that we got, where t could be any number. So if t was 0, this would be the 0 vector, but t could also be anything else, and then it would not all be zeros. So this is linearly dependent, and to come up with an answer to the follow-up question, I just have to choose something for t. Again, if I choose t equals 0, that'll be silly because that won't give me a non-trivial linear combination. That would give me that they're all 0. But I'll just set t to be anything else. So my favorite number is 1. So then x1 is negative 2, x2 is 3, x3 is 1, and then let me write, here is my linear combination. It's x1 times the first vector, x2 times the second vector. Oops. I'm not writing it down correctly, but this is the 0 vector. Maybe I should write. Maybe that's better. Okay, but we got it. All right. So let me do another one out of chapter 4. Finding a basis for a solution space. So I wrote, this is a 5x3 system of equations. Of course, the first thing I'm going to do is put this in a matrix. So 1, 1, 2, negative 1, 1, 0, 1, 2, negative 1, negative 2, 1, 0, 2, 3, 2, 1, negative 1, 0. Right? I already have a 1 here, that's great. I want zeros underneath it. I'm going to do row 2 minus row 1, row 3 minus 2 row 1. Let's see what happens. Top row doesn't change. This is now a 0, 1, -3, -1, right? -2 minus -1, yeah. 0, 0. This is 0, 1, -2, because I'm subtracting 2 row 1. This would be +3, -3, 0. Okay. The next thing I would want is a 1 here, which I already have, so that's good. Then I would want, and again, I can do this problem if I only go for echelon form, meaning I get zeros below the ones. It's going to be easier if I actually go for reduced row echelon form. So I'm going to get a 0 here and here. So I'm going to do row 1 minus row 2. And row 3 minus row 2. So 1, 0, 5, 0, 1, 0. Second row doesn't change. Zero, 0, 1, 4, -3, 0. Okay, doing pretty good. The next thing I would want is a 1 here. I'm getting lucky with these 1s. But I want this to be in reduced row echelon form, so I would want zeros. I mean, there's nothing below, but I would want zeros above this 1. So row 1 minus 5, row 3, and row 2 plus 3, row 3. After this, I'll be done with the matrices. Because I got it in reduced row echelon form, I'll just be able to read the answer right off very easily. So this is 1, 0, 0. So 0 minus 5 times 4 is -20. 1 plus 15 is 16. 0, 1, 0. -1 plus 12 is 11. 0 plus -9 is -9. This one doesn't change. Yeah. Okay, so it's in reduced row echelon form. I've got a free variable here and here. So this is x4, this is x5. I'm going to set x4 to s, x5 to t, and then x1, x2, and x3 I can get by solving these, and I can read these answers right off. x1 is, so I switch the signs on these, so it's going to be 20s minus 16t. x2 is -11s plus 9t. x3 is -4s plus 3t. I can put my answer together. My answer is going to have an s part and a t part. I'll pull the s out of the s part and the t out of the t part, and then those two vectors that are left over after pulling out the s and the t, that's going to be my basis. So that's what's going to happen. I just have to do it. Let me make sure to put these in the right order. x1 goes on top, and x2, and x3, and x4, and then x5. I won't belabor this. Like I was saying, there's an S part and a T part. Let me collect all the coefficients of S. 20, negative 11, negative 4, 1, 0, right? Because this one doesn't have any S. Let me collect all the T parts. Negative 16, 9, 3, 0, 1. That's how we do this. And then the basis is a set consisting of this vector and this vector. I'm okay with it if you just draw arrows pointing to this and write the word basis, but formally, as a mathematician, I should carefully write it in the correct format. This is the basis of the solution space.